Artists use a stippling technique called inversion. They fill regions with very dense black stipples, to generate solid black color, and leave white gaps for negative space effects. In this paper, we mimic this technique to improve the visual quality of computer-generated stipple illustrations. Our key idea is to use both black stipples and white stipples together, to explicitly render the positive and negative space, and fill up the background with stipples for inverting areas. We call this idea inverted stippling. This allows us to stipple beautiful images, that can preserve the structure and fine details in dark areas well. However, inverted stippling is challenging, as there are two classes. Therefore, we need a multi-class stippling method. To address this, we present an extension of Lindabuzo-Gray stippling by Doosan et al. We call this extension, multi-class Lindabuzo-Gray stippling. The idea of our MLBG is to use multiple layers. Given a source image, we first create an inverted version of it. These are density maps for each of the layers. Then we can stipple in each layer and couple them together. A simple way is to stipple these layers individually and then combine the final results. However, it doesn't work well, because we cannot obtain an inter-class blue noise property by combining independently created stipples. To solve this problem, we couple the layers in intermediate steps with their associated Voronoi diagrams. The idea works like this. Given two layers, we can create two within-class Voronoi diagrams. We can also couple the stipples together and then create an inter-class Voronoi diagram. Now, for each stipple, we can compute two new centroids. One is from its within-class Voronoi diagram, the other from the inter-class Voronoi diagram of all stipples. When we move the stipple to the centroid of its within-class Voronoi diagram, it enhances the within-class blue noise property. When we move it to the centroid of the inter-class one, it enhances the inter-class blue noise property. Therefore, in each iteration, we randomly select one centroid and move the stipple to that position. This allows us to balance the local and global blue noise properties. According to our experiments, we found that an adaptive probability based on the stipple density works best. Lower density stipples should move often to local centroid, and higher density stipples should move often toward the global one. The reason is that, in inverted stippling, high-density stipples often hide in the filled background. Only the lower-density stipples are visible, and hence, their local blue noise property contributes more to the visual quality. On the other hand, the higher-density stipples consider the global blue noise property, to keep away from low-density stipples and avoid overlap. Our MLBG generates good multi-class stipple distribution. However, the results are still not inverted stippling. We need to fill the background by adding new stipples as artists do. To do so, we introduce a stipple-based background filling method. First, we render all the foreground stipples in white on a black background to obtain a new density map. Then we perform another pass of stippling, to add new stipples at the back of the original one to fill the background. Now let us show you some results. This is a result of our inverted stippling. As you can see, the black background and the structure of the whiskers are well preserved. Here is another result. This man face is a stippling example also used by previous works. Besides black and white, our MLBG allows us to create stippling with multiple colors and shapes. Our MLBG inherits the temporal coherence property from LBG. It can automatically refine the stipple number, as shown in this animation. MLBG is a multi-class blue noise sampling method which is temporally coherent, and with adaptive sampling number. Our MLBG can be used in many applications, such as object distribution, vector field visualization, visualization with transparency, and multivariate demographic map. Thank you.